Okay? There's no page number,
Strength
but it's page
derivative
3.
control.
So just write down, okay, that you have to know page 3 of PID controller design text. Alright? And I strongly encourage you to actually go through the rest. Okay, because in Glasgow we encourage an independent learning culture, right? Okay? So this is very important, yes, and the rest still go through, okay? Alright, so page 3 you have to know. The slides are just a summary of the text. So let's go to the slides. Okay, so in PID controller design slides, what do we do in our PID controller design? Alright, recall that our loop transfer function L is C. Yes? Okay? So what does the design of a PID controller involve? It involves the shaping of the loop, because you can't change your plan. The plan is fixed. Right? So how you design your controller, it involves the shaping of this loop L. And if you look shape the L, all you do is actually you modify this shape to achieve some design performance. And what do you wish to achieve your design? You wish to achieve performance, which is like following the command response well, close to stability, disturbance attenuation. These are performance criteria. Okay, you also wish to achieve robustness, okay, with respect to stability and performance. Alright, so we say that for performance, how does that relate to the loop L? We want to increase the bandwidth of the closed system. Okay, so what you increase that? What you do is you increase the crossover frequency. So we still remember for the Nyquist plot for control string, there's this term called crossover frequency. Okay, the gain L. So if you change the crossover frequency, you can change the closed loop bandwidth, which is the operating frequency range of the closed system. Alright, and all these targets once again, they can be translated into requirements for sensitivity function and complementarity. Yeah? Because S is 1 over 1 plus L. T is L over 1 plus L. So if you have got requirements of L, yeah, you want to keep L, like, for instance, you want to keep alpha away from minus 1. You want to keep 1 over alpha away from minus 1. And all these translate into requirements for your S and T. You understand that? Yeah? So an example for Nyquist plot, L is 5 over S plus 29, S plus 1. So you can take out this, which is not available in the notes. So this dot here, which is the intersection of the Nyquist plot with the negative axis, is omega m, called the gain crossover frequency. And the intersection of the Nyquist plot here with the unit circle is omega c, which is called the phase crossover frequency. Okay, so if you were to change these frequencies, you practically can change the closed loop bandwidth. Yeah? Okay, the next question you might have is, how does this relate to closed loop bandwidth? Okay, are you done with this? No? This dot here is omega m, gain crossover frequency. I'm reading this because I think most of you cannot read my handwriting. I've got bad handwriting. I know that. And this dot here is omega c, which is phase crossover frequency. Alright? And this is the omega increases. And you know they say that doctors don't have good handwriting. I'm not a medical doctor. I have bad handwriting. Okay. Right. Let's move on. If you're asking me, okay, how does this relate to what? Again? Sorry? You have a question? Oh no. If you don't have a question, don't do this. Okay. I have a question. Okay, wait. Stop. Right. How does that, okay, how does those two relate to closed loop bandwidth? Okay, focus. So if you have your magnitude and your phase in the Bode plot, right? Okay? You can find the gain margin, which relates to your gain crossover frequency, and the phase margin, which relates to your phase crossover frequency. Yes? Alright? So if you can shift the gain margin and the phase margin, okay? Effectively, how do you shift the gain margin and phase margin? You either shift your gain up or down, right? Yes? Right now. If you want to shift your gain margin, right? You shift your gain up or down, right? Yes? Because when you shift it up, you make the gain margin smaller. Shift it down, you make the gain margin wider. Phase margin, you shift it left or right? or up or down. Right? Yes? And if you shift this, arbitrarily if you shift this, you're going to change the bandwidth. What is bandwidth? Bandwidth is minus 3 dB away from 0 point. Okay, so if you shift L, up or down, you're going to change your bandwidth. Okay, and the bandwidth is the frequency range that the closed system can operate. Okay? Understand that? Alright? So how do you shift L? How do you shift it up or down, or left or right? Up or down is just multiplying by the magnitude, yes? So just multiply by Kp, proportional gain. How do you shift it left or right? How do you change the phase? You either introduce an additional delay, or you introduce a derivative function. Okay, you introduce form of S or introduce S. So you can shift the phase. Okay, then what is all this? All this translates into a PID controller. Okay? Because in a PID controller, I think this came out. I don't recall whether last year or the year before the last one. First of all, what is a PID controller? Write down this. So UT is KPET. If you don't trust me, you can look up the past year exam questions. Yeah, I don't think I'm always trying. Oh yeah, this is related. You don't remember what this is really related. Okay. U is KPET. Okay, proportional gain times error. Y times error because U is over here. The PID controller C bracket S is over here, and the input to the controller is E. Alright? Okay? So your PID controller C is Kp proportional gain plus Ki over S. Here we have that integral gain plus Kd times S, where Kd is the derivative gain. Okay, so Kp has shaped your proportional gain. Yeah? If you take out the factor out, okay, you practically see a proportional gain. You can push your L up or down. And what does 1 over S and S do? It changes your phase. Okay? Alright? There are some words that I scribbled, very small, which is what I'm trying to summarize what is in the notes that I just told you to read. Okay, otherwise there's basically no information in this set. I was trying to verify. So if you want to copy, go ahead. If you don't want to copy, just read the text. Okay? Okay, so proportional control, U is K times E. Okay, so the control vector CP is your proportional gain K. Alright? The contribution to your control signal is based on instantaneous error. Okay, if you use this alone, alright, we say that performance is limited and you end up with non-zero steady state error. Alright? So if those who recall for the DC motor set and experimentally last year, if you just use proportional gain, you still have some steady state error. Alright? Integral control, okay, which is U goes to K over T, the integral, you can integrate your error over a certain period of time. In Laplace, after Laplace transform in frequency domain, okay, the control factor Ci will be K over Is. Alright? And for integral control, we say that definitely can see obvious that output is proportional to accumulated error because it's an integral, right? So this relates to slow reaction control mode because you only react output, you only react and accumulated amount of errors. Okay, so this is slow reaction. Alright? It forces the steady state error to 0 if you have a step response and disturbance. Okay? Derivative control, UD is KD times the derivative of the error. And if you do the Laplace transform, you end up CD, which is K times TD times S. Alright? So the output is proportional. Rate of change, control error. I would say that this reacts to fast mode. Because you can imagine your control error may go up and down, up and down, up and down. Right? So if you take the derivative, it goes positive, negative, positive, negative. And this is very fast changing. Okay? So it's a very fast reaction. Alright? But if your error is constant, it doesn't go up and down, it's constant. If your error is constant, E dot is 0. Okay? So if you have constant error, derivative control does nothing. Okay? If you have constant error, you should use integral control. Okay? If you have fast changing errors like up, down, these are E. So the derivative goes positive and negative. Okay? This is when you use derivative control. Understand that? Because if E is constant, E dot is constant, E dot is 0. If E dot is 0, UT is 0. Okay, so in constant state is error. Derivative control does nothing. It's useless. Alright, to deal with constant state error, use integral control. Okay? Alright? I think there's a missing K here in your slides. So in the exam, if you were to answer this, at least you get some marks. But if you try to memorize the text and everything, then you answer in full sentences, then you get higher marks. I'm not trying to say that this will come up this year, okay? I'm just telling you that this has appeared before. Alright? Okay, can we continue? Yeah? Alright, so this is nothing, it's just a recollection. Alright, CS, which is a PID controller. What you can do is you can factor out K. So if you factor out the K, you end up 1 plus 1 over TIS plus TDS. Okay? You factor out the S, you end up this and this. Alright, and we observe that in TD is much smaller than TI. Okay? If TD is much smaller than TI, you can factor out in this and this. Alright, basically what we're telling you is that you can view the controller, the PID controller as K over S times something that increases in phase, because the integral has a constant phase here. Okay, this can increase in phase over time. Alright, similarly with this. This is more like phase E than this one like this. Okay? Alright? Just an example from a MATLAB simulation. Okay, so in MATLAB simulation, you can actually plot the Bode diagram of controller, of PID controller. All you need to do is just key in this in MATLAB, okay, and then put in the numbers for K, TI, and TD. So for those who are interested, try out MATLAB. You can key this equation, okay, and then specify your range for frequency S. Then put in values for K, TI, and then you say plot Bode diagram for CS. And what you get is this. Okay, the result does tell you that for a range of frequencies, the magnitude of the PID controller is not constant. Okay, the phase is also not constant. Alright, and you can make use of this to actually shake the loop, because L is C plus P. Okay, so if you draw your P on top, and you draw the multiplication of C and P, you can see that you can effectively shape the shape of L across the frequency range. Okay, so this is what we're going to do here. Plot P and C on top of each other. So the line in blue is P. Okay, for those who have got that, I know. The line at the bottom is P. The line in the middle is L. And the line on top is C. Okay? For phase, if you look at the low frequencies, the line on top is P. The line in the middle is C. And the line at the bottom is L. Alright? So as what I've just said, you're going to key in your controller in MATLAB, you key in your plant in MATLAB, you plot the Bode plot for C and P, and you plot the Bode plot for C plus P. This is what you get. Okay? So you can see that C looks very strange. The line on top looks very strange, right? It's a U shape. Yeah? Your plant is the one at the bottom. And when you multiply them together, you get the one in the middle. Yeah? And the one in the middle, the intersection with 0 dB, shows shows you very clearly the bandwidth of L. Okay? So if you draw the 0 degree line here, okay, cross, and you look at L, because L is what we are interested in. Because our gain margin, phase on the magnetic plot, gain margin, and also the bandwidth. Okay, so the bandwidth is minus 3 dB away, so you just draw minus 3 dB. And you know that it's here, and this point is your bandwidth, EW. Okay, bandwidth. Alright. Okay, and from a Nyquist plot, if you look at the intersection of L, you can draw a Nyquist plot like that. If you look at the intersection of L, you can find the gain crossover frequency, then you can find the gain margin. Alright, so in MATLAB, this is how you design the loop L, and also the controller CS. Okay, so in MATLAB, after you have the C and the P, then compare them together, you get L, or the gain and the benefit and phase. Okay, then you can plot like this plot. Find out what's the gain crossover frequency and phase crossover frequency. Okay, and from here you can see your value. So if you're not happy with your value, if you're not happy with gain crossover and phase crossover, what do you change? CS. Okay, you don't change P. Alright, if you're not happy with your gain crossover, phase crossover frequencies, you're not happy with your bandwidth, you change CS. And what do you change? You change your KP, KI, KP. Alright? Okay? So if you want your time response to be faster, you can increase your KP. Okay? Push it up faster. You want zero steady state error, you increase your KI. You want get rid of fast changing errors, you increase your KP. Understand? Alright, that's the order. So this is all about PID controller. Okay? The next very important part of this course is on pole placement design.
Oh, this after C.
Without fail, pole placement design will always come out in a portion of a question or two questions. Alright? So that's how important it is.
Yeah, wait, again. This is different, you don't go down. This is the P. Yeah. P is the button. Wow.
Okay? So ready? Alright.
Yeah.
This is our usual 2 degree of freedom control structure. But then now there's no F. So this is only 1 degree of freedom. Because there's only C here. Alright, there's no F. We got rid of that for simplification purposes. Okay? So just take note that Y, output Y, is CP0 over 1 plus CP0 times R. Okay? And now that you have understood that C is not just a proportional gain, okay? It's a PID controller. Okay, and what's a PID controller? Basically, if you were to lump everything together, there's a numerator and a denominator. It's just a transfer function. Alright? So a PID controller is just a transfer function. Transfer function has a numerator and a denominator. Okay? And we call CS GS over HS. Okay? The plant is also a transfer function. Called E0, D0 over E0. Alright? And the rest still remains the same. P is UCP over 1 plus CP, S is still 1 over 1 plus CP. Okay? You note that the denominator are both 1 plus CP. Yeah? And remember, the last time in dynamics and control 3, we told you that the closed transfer function, which is the relationship between Y and R. Okay? In this case, CP over 1 plus CP. Alright, if you take the denominator, equate that to 0, what do you call that? Call that a characteristic equation. Okay? So, if you're asked to produce the characteristic equation, the characteristic equation is 1 plus CP. And if you solve that, put this to 0, you find the closed loop holes. Okay? So if you put 1 plus CP to 0, you find
There is
the
one inside.
Alright? Okay?
This is dynamic and
If you go to root locus,
control.
alright? Remember that L is CP naught. Okay? You can rewrite that. If you're happy, you can change C to KC naught. So it becomes KC naught. And your characteristic equation is 1 plus CP is 1 plus L is 1 plus KC naught. So we say that given the controller CS, which is KC naught S, where K is a variable gain and C naught is a constant controller. Alright, the root locus is the loci of the values of S for which the characteristic equation equals to 0. Why? Because root locus will tell you closed loop holes. Yes? Okay, if you still remember root locus, do you remember root locus? Open loop holes will tend to open loop 0. Remember that? Okay, and whatever is remaining, you have to find where's the capital one. Okay? That's the closed loop locus part. All in all, it calls the closed loop holes. Yeah? So what I solved is 1 plus KC naught equal to 0. As K changes from 0 to 2. Alright, the example is this. So if you remember this from the lab, we did the last time. Why is this important? Because at the end of the day, what we are telling you, okay, is 1 plus CP, and 1 plus CP is a characteristic equation. If you equate 1 plus CP equals to 0, you end up with closed loop holes. And in MATLAB, you can get these closed loop holes using the root locus for different values of K. Okay? Alright, so that is just explanation. This is what is really the core, the material we are going to cover. Okay, so back to this. We are writing CS as GS or HS. P naught as B naught or A naught. Okay, so we also have to start update ourselves, right? The closed loop transfer function is not just CP or 1 plus CP. It should be, if you put this and this inside here, you end up with B naught G over A naught H plus B naught G. Alright? Just substitute. Okay? And you update your complementary sensitivity function T and sensitivity function S. You end up with B naught G over A naught H plus B naught G, A naught H over A naught H plus B naught G. See that the denominator is still the same. Okay, and now we call it a new term instead of characteristic equation, which is 1 plus CP. A new term is characteristic polynomial. Okay, characteristic polynomial is A naught H plus B naught G. Same thing. So if you want to close loop holes, you can take A naught H plus B naught G equals to 0. You will solve that. We have another name for this. We call A naught H plus B naught G characteristic polynomial. We call it ACL. Okay, so ACL is A naught H plus B naught G, and we call it Diophantine equation. Okay, so in the exam, you will be asked to write down what is the characteristic polynomial. Okay, so what I write down is this. Alright? So now that you know this, what do you do? Okay, so in pole placement design, you work with the Diophantine equation to design your controller C. Okay? How do you design a controller C? You design what is G, and you design what is H. Okay? So the aim is to select the controller parameters G and H in a way that ACL, which is A naught H plus B naught G, is placed in specific locations. So you want to place your closed loop holes in a certain location. Why? Because the position of the closed loop hole will tell me the dynamic response here. Alright? If I have imaginary holes, I have oscillations. If I have real holes, I go to the steady state value very quickly. But it depends. If my real holes are very far away, very negatively far away, I go to the steady state error instantaneously. If my real holes are very near the imaginary axis, I have a bit sluggish response. So the placement of the closed loop hole is very important, right? And we very often when we design, we want specific response. So some systems we don't want it to behave too fast. Some systems we want any overshoot. So we want to place them specifically in a certain location. And you know that the roots of the characteristic polynomial, which is a naught h plus b naught g, are the poles of S and T, because they share the same denominator, a naught h plus b naught g. Alright? Next is the motivation part. Now, why do you want to place pole? As I said, sometimes you want to influence the right time. Sometimes you want to influence the overshoot. Sometimes you want to influence what do you call it? TS, the settling time. Yeah? Okay, and this is given to you. And why is this important? Because in the question, we often tell you that design CS such that rise time is 0.5. Overshoot is 1%, and settling time is 2 seconds. Alright? So from there you can actually do your design. Okay, this is the slide that scares a lot of students the most. Okay? And this is the last slide. It basically tells you everything you need to do. Okay? It's just a procedure, it's a summary of procedure. Alright? Okay, and there's 2 stars. Go through page 3 to 5. You can't see the star. Okay, 3 to 5 of both placements. Just go through, right? To get some exposure. Okay, so recall that ACL, which is a characteristic polynomial, is A naught H plus B naught G. The plant P is E naught A naught, controller is G over H. So what does it tell you? I'll just read that. But don't worry, because none of you will register what I read. Serious. Okay? I'll give you some examples that I've given your seniors as well. And this will be available on Google. Click on the copy. Okay? So, but I will just cover the summary, alright? So, if you have a reference performance specification or rise time overshoot, I tell you rise time is 0.2 seconds, overshoot is 1%. Okay? Calculate ACL. Okay? Basically, for a second order system, if you know TR and you know LT, you can form the second order tensor function. Alright? And you know the denominator and you know ACL. Okay? Based on whether you want a proper controller or strictly proper controller, and whether you want integral action, you select the order of G and H or controller. So is it the order, second order, first order, and the order of ACL, which is a characteristic polynomial. So if your ACL is bigger than 2, and all you have is rise time overshoot for second order transfer function, you need additional poles. You select them far away from the dominant poles. No, nobody can understand this exactly, right? Never mind. Okay? Then you calculate the parameters for H and G for a controller by solving the diagonal equation. Okay, and then with the F, check S and T, the sensitivity functions, evaluate your controller performance and robustness. Not nice, change your modification and redesign. Okay, nobody can understand this, yeah? If you can understand this, let me know. Okay, so what are you supposed to do? It will be very clear if you read page 3 to 5, the notes, but not many of you will read. And you can't read it now. So, okay, once again, I've just enabled this in Google. You don't have to copy if you don't want to. Feel free to copy if you want to, but I'm not going to slow down if you are copying, so you can continue copying. Okay, let me just go through this. So we said that you can design for a proper controller or strictly proper controller or with integral action. Yes? These three are different controller designs. Okay, so if you want to design for a proper controller, what is the steps that you should observe? First of all, plant P is B over A, controller C is G over H. So example, if your plant is a second order plant, 1 over S squared plus 2. So what is B? B naught? B naught is 1. A naught is S squared plus 2. Okay? The next question. You think that the degree, the order of B naught, okay, the degree of B naught is 0. Okay? Because B naught is S to the power 0. Alright? The degree of A naught, the denominator is 2. Because the highest order is S to the power 2. Okay, and here we say N is equal to 2. So, as a guideline, tell you that for a proper controller, the degree of G is equal to the degree of H, which is equal to N minus 1. So this is a guideline I will give you, right? Okay? So now you know the order of P, because it's given, it's 1. For P, you know the order of B, you know the order of A. And from this, we tell you that the proper controller has one order lower than that, the plant. Okay? So when you design your GS and HS, it has to be one order lower. Okay? So we say that CS is G1S plus G0 over S plus H0. Okay? Observe that the denominator does not H1 because we want to only HS. Only HS means the highest order coefficient of 1. Okay? But do you agree that this is order of 1? Do you agree that this has a degree of 1? Yes? Because the highest order is S. Alright? Next. Okay? You know that ACL is A naught H plus B naught G. This is your diagonal equation. So what you do? You find out what's the degree of ACL first. Okay? So the degree of ACL is the degree of A naught H plus B naught G. What's the degree of A naught H? Okay? The degree of A naught is N. So it's N. The degree of H is one order smaller. So after you take A times H, if you take something that is S squared, okay, times H at the end of the day, alright, you take this times this plus B naught times G, okay, what you end up with is a degree of N minus 1. Alright, and if you know this, what is N? N is 2, so 4 minus 1 is 4 minus 1 is 3. So you know that ACL has a degree of 3. Okay, if ACL has a degree of 3, then you imagine what it is. Alright? So you can form ACL, which is S squared plus 2 zeta omega n s plus omega n squared for second order Dirichlet function. So we say here that this has got 2 dominant poles. But then your degree of ACL is 3, right? So you need one more pole. So what do you select? You select a pole far, far away. Okay? Where P is large. So at the end of the day, when you look at this, at the end of the day, P will disappear. It will just disappear. Alright? And the dominant poles are this. Whereby you can specify a rise time and overshoot. Okay? So if you know this, and you are given a rise time and overshoot, you know omega n and zeta. You can form ACL. Okay? Next. Because you also know that ACL is A naught H plus B naught G. So initially you have this one, equation 1. You also know that ACL is A naught H plus B naught G. So you substitute A naught, which is S squared plus 2. You substitute H, which is S plus H naught. You substitute B naught, which is G1S plus G naught. B naught is 1. You substitute G, which is G1S plus G naught. And then you can expand. Okay? And then this equation 2, you compare coefficients between equation 1 and equation 2. Okay? Compare coefficients and you identify what is G1, G0, and H0. Okay? This is for a proper controller. Alright? Basically, what you do is first, you identify the order of your plant, identify the order of B naught, identify the order of A naught. Alright, with that, you know that you want to design a proper controller. You identify the order of a controller, C. Okay? And then, from there, you can check the order of your ACL. So you know that you need to form a third order polynomial. Alright, if you are given a right time and overshoot, you know your second order polynomial here, which is another pole far away, so it disappears. Now that you've got this, and you know ACL is A naught H plus B naught G, just substitute A naught H B and B naught G inside, and compare these two equations, compare the coefficients, and you get your controller parameters. Okay? So this is for a proper controller. Alright? For a strictly proper controller, you need a copy. Okay. I'll just leave it here for a while. But seriously, it's on Moodle. It's already on Moodle. Okay, so just leave enough space at the bottom. You can read it. Alright? Okay? So let's move on. We have gone through our proper controller. What about a strictly proper controller? Okay? So for a strictly proper controller, what does it mean strictly proper? What it means is that the controller numerator, order of the numerator must be smaller than the order of the denominator. Strictly proper. So for those who have learned strictly proper fractions, like strictly proper transfer functions or anything that's strictly proper, the numerator must be one order smaller than the denominator. Okay? So it tells you that the degree of GS is n minus 1, the degree of HS is n. So that's the guideline there. Okay, for example, if E naught is 1 over S squared, so obviously n is 2, because the highest order is 2. The controller, the numerator will have order 1, so it's G1S plus G0. Denominator is order 2, S squared plus H1S plus H0. There's no H2, because denominator has been unit. Means the coefficient of the highest power is 1. Okay, from this, you can check the order of ACL before.
Angry. You.
Because A naught has order 2, H has order 2, so it's 4. Okay, and you are told to design postcode poles at this location. Okay, this is all you're doing. Alright, so you're supposed to design C, which is design your G and H, so that postcode poles are at this location. Okay, how do you do this? You are given 4 poles, okay? 2 set of imaginary poles. So with 2 set of imaginary poles, you need to learn how to form your closed loop characteristic polynomial. Alright? So if you have one set of pole, A plus minus JB, and the other set is C plus minus JD. So what you do is bracket S minus A plus JB times S minus A minus JB, S minus C plus JB, times S minus C minus JB to 0. Then what happens next? If you are very careful, you get the right solution. Okay? So this is what you should do. Right? Be careful. And you try to expand. So I don't need to copy, right? Expand. And get like this. Okay? S to the power 4 plus 11 S cubed plus 60.5 S squared plus 55 S plus 25. And that's equation 1. Okay? This is the closed loop polynomial for your desired closed loop pole. Okay? Equation 1. How do you form equation 2? You form equation 2 by saying that ACL is A naught H plus B naught G. Alright? Because plan is 1 over S squared. The plan is 1 over S squared. So B naught is 1, A naught is S squared. Okay? We have identified the degree of G is 1, so it's G1S plus G naught. The degree of H is 2, so it's S squared plus H1S plus H naught. Okay? Expand. So you get this. S to the power 4 plus H1 S cubed plus H naught S squared plus G1S plus G naught is equation 2. Equation 1, equation 2, what you do next? Compare the coefficients. Okay? So basically, equating 1 and 2, H1 is 11. See that? Yes? H naught is 60.5. Okay, G1 is 55 and G0 is 35. That's all. Okay, so this is your CS. Alright, 55 S plus 35 S cubed S squared plus S plus Q. Alright? So this is strictly for controlling. Okay, what are the steps? First, if you are given right time to overshoot, okay, use S squared plus 2 zeta omega ns plus omega s squared from your second order differential. Depending on the order, you will write the three order, the order ACL, just put one more. If you are given exactly the closed co-location, okay, exactly the closed co-location, just multiply out the end of the ACL. It's equation 1. Step 1. This is step 1. Okay? Step 2, ACL is A naught H plus B naught G. Okay? So expand that. That's step 2. Step 3, let's compare the coefficients. 3 steps. Alright, of course there are details in between them. Okay? So we'll go through the design for a proper controller, the design for strictly proper controller. What about integral action? Okay, so if you want to include integral action, if you want to include integral action, basically it means that for a controller CS, okay, your denominator, alright, you can draw pure integrator out of the denominator. You understand this? Integral action means there's a pure integrator that can take out for the denominator. Alright? So all you need to do is write your CS to be GS over S times H prime S. Okay? Why do you write it like that? Because it tells you that you can draw a pure integrator out from the denominator. Okay? You move the integral term to PS. Alright, and you get PS equals to 1 over S E naught. Because end of the day it's just C. So we can move the integral term. The end of this and this. So an example, if you have P naught is 3 over S plus 1 plus S plus 3, the highest order is 2. Okay? I will tell you that the controller C prime can be improper. It's fine if it's improper. Okay? Because when you shift the integral term back, this, your CS is actually proper. Alright? Because if you shift the integral term back here, your denominator will be 1 order higher. Okay, so it's fine, improper. Okay? And your design, the guideline is your degree of G, is N, and degree of H prime is N. So if you follow the guideline, so one thing you need to memorize, what do you need to memorize? You memorize the guidelines. So you know how to set order of G and H. Okay, even best if you understand how the guideline comes about. So then you can first. Okay? Alright, so if you notice, the order of G is 2, the order of H is 1, so end like this. Okay, as we said before, you find out what's the order of ACL. It's 4, because A naught has an order 2, H has an order, A naught has an order, here. A naught will have order 3, because there's an integrator over there. Then H will have order 1 more, so it's 4. Okay? I will tell you that you have desired those locations here and here. Alright, let's again expand out the same as the previous example. So equation 1 here. The diagonal equation ACL is A naught H plus B naught G. Okay, that's one here. That's equation 2. So we form equation 1, equation 2, and you equate the coefficients. Alright, and you end up with the coefficients for your G1, G2, G0, G. Like that. So just form 2 equations and compare the coefficients. What do you need to do after this step? Huh? No. What you need to do is, although you do not need to copy, although you did not need to copy, but you did not get to practice. Okay? You did not have to copy because I told you that copy is to follow, right? But you did not get to practice. So what you need to do after this lecture is you need to, okay? Do you want to practice? Huh? Do you want to practice? Okay, I will just leave it open now. What I'm going to do now is this. There's another example here. Okay, I'm going to make it here. With a lot of cards, a lot of keys. Okay, I'm leaving this open. So whoever wants to practice, stay. And you try this. Whoever wants to leave, feel free. Okay, right now, but please tell me your attendance, please check first. Okay, whoever wants to practice, try this. Then we can do this for like 10 minutes. Because there are keys there. Whoever wants to leave, feel free. Okay?